Hello friends, welcome back to the bench. Our patient is our tool. So what we want to do is modify this so it's more usable than it is coming from the factory. Now there are fair issues in design of this, and let's analyze it. So today what we want to do is disassemble it, learn how it's learn how it's built and how we can improve it. But first let's identify the issues that we have with it. So this is another form of heat plate, preheater, but obviously this is tiny, right? It works great. But you can see that thermal feedback is connected to the plate, then the plate is connected to another plate, which is connected to another plate, which is connected to the actual device, which means we have a fair bit of insulation from the electronics, and the heat obviously goes up, so it's not going to be traveling as well down here. It will obviously, if we set it to 400 degrees, it will eventually get hot, too hot. So obviously it's just a matter of time, but it's more than enough to actually use this and not overheat it. So far I have not overheated this, but it heats up really quickly and it holds temperature really nicely. So for my needs it's maybe 5 minutes, maybe 10 minutes tops that I keep this on. Now on this one, the heating element is here. We set it to 400 degrees, which it rises to 400 degrees and holds the temperature. However, this heat plate heats up only to about 280 degrees, which means 400 degrees is inside the device. That in turn, that and the fact that our heat plate is over here, this whole plate heats up. 400 is inside, so the bottom heats up pretty well, and the entire desk heats up to the point where these mats are deforming from the heat, because that's what they do. If you overheat them, they will deform. They will go back to their original shape, more or less, depending on how much you overheated it. So that is the major issue with this device. I've heard of mods that basically you just remove the thermistor that I can see is connecting over there to the bottom of the heat plate, and you route it outside and put it on the board. Then the thermal feedback is actually from the board. Fine, but that still doesn't resolve the problem of the entire device heating. So ideally we want to somehow insulate the heating element so it doesn't heat the rest of the device. And I have few ideas how to do it with household items like aluminum foil, but first we need to see what's inside. So first let's disassemble it and see what we can work with. Okay, so this is interesting. So we have this big separator here, so the electronics don't heat up. A little heat shield with some notches over here. Not sure why that is. We have a supply line that goes here to the electronics. It looks like we have two transistors. That's probably a microcontroller. I would bet it's Atmel AVR core microcontroller. Potentiometer, obviously, and the feedback goes here. The transformer is output is 10 volts, a quarter amp. Interesting. Alright, it's very interesting that the device is not very powerful. Personally, I was expecting a power converter, not a transformer. But the benefit of the transformer versus power converter is that it produces a lot less interference back to the network. It also provides good insulation, the galvanic isolation from the source. So there are some positives of using a transformer. Obviously it's gonna be heavier, but we're working with 10 volts, so this is 10 volts AC, right? So once we smooth it to DC, and perhaps, no, maybe we are actually using AC, could be, meaning that these are not transistors over here, but instead these are thyristors. Oh, we have unoccupied connector here, and we have adjustment on this, so this is probably to calibrate it. Now what we're actually interested in is underneath the heater. So let's take the heater off and see what we have over there. This is our heater with thermal feedback in here. Now let's disconnect it completely and see if we can remove the heater. However, do we need to remove the heater? Yeah, I would like to remove the thermal feedback. It looks like it's held by two kind of like a shims. So we just need to pull them from both sides, but they are glued together with some kind of glue. Looks like silicone. Yeah, that's the only kind of glue that would make sense here. A high temperature silicone, because any other glue is gonna grow weak in this temperature, but looks like the silicone is very weak as well. Because what we want to do is remove the thermal feedback, and actually, oh, never mind. Okay. All right, take a look at this. That's our thermal feedback. It's a thermistor, tiny one. It actually doesn't even look like a thermistor, but I believe it. And I just managed to pull it out from here. So we have our thermal feedback outside. So that brings us closer to our goal. We can route it outside now and get the temperature of the board instead of the temperature of the heater. And the idea in my head is already forming. So what if we remove this mesh, then put this on top, then I can put back the rails again, and it should be roughly the same size. I need to confirm that though. Okay, it is a little too fake, right, for it to go exactly as it went before. But let's see how much. We need to find a longer screw, but I will not have a longer screw than that. We could drill a little bit through here. That could also work. Let's see if I have anything longer than this. And we would have to lift it by a lot. So this would have to be a very long screw. So this is roughly how much we have to lift it for the rails to work. That's a lot. That is indeed a lot. Another option I was thinking was to drill the holes here so I can install it like this, right? Then the heating element can go back inside. The thermistor can go outside, and we're golden. Let's give it a quick test to make sure that a thermistor is still working. If not, that shouldn't be a big issue. We can replace the thermistor with maybe a better one. That's not a problem. The only function this element has in this whole circuit is that it changes resistance based on the temperature. That's what gives you a thermal feedback. It's a very simple device, and every resistor works a little bit like thermistor. This is not desired behavior in the resistor, obviously, but you have characteristics of in the data sheet. If you find one for the resistor, you have the typical characteristics, how the resistance changes based on the temperature, and the resistance drops a little as the resistor heats up. In this case, we're talking about temperatures 400 degrees. Obviously, I'm not going to be heating anything up to 400 degrees. Now I do, because that only gives me 280 degrees here, or 260 degrees, and then the board heats up to maybe 130 tops. Right? So I set it to 400 degrees, but if this monitors the temperature of the board, there's no need to heat it up to 400 degrees. There's not even a need to heat it to 260 degrees. 150 should be maybe 160 tops. It shouldn't be more. The recommended temperatures that I see on other channels is 120 and 130, 120. And that's roughly what I get on my boards, but that's the highest temperature I can actually achieve. Now the reason we're doing this is because I have the board that I messed up, and I have suspicions why I messed it up, but I ripped about 5 pins. So now we have 5 pads. So now we have to restore those pads and resolder the socket on it. But for that, I need a little better device than I have right now, and that's why we're working on this. So let's see if it works. We have set it to 50 degrees. It's 32 over here. It's heating up. Okay, it's rising slowly. There's 50. It grew very quickly. Okay, so the heating element works. The thermal feedback works. So the device is working. Now it heats up pretty quickly, I would say. Very nicely. So I'll have to think about how to raise this so we have a nice holder. In addition, I would like it to support larger boards, because right now it's perfect for ECMs but not for motherboards, and I have some motherboards coming for repairs, so I would like to have the ability to put a bigger board in it and still hold it nicely, because so far I've been just using these screws and just screw it in, because it's kind of important for the board to be relatively steady, not shaking around and stuff, especially when you're soldering a socket with this many connectors on it. So let's do the test before we call it a day. So what I did is I put the thermal feedback on the board. It is stuck with the Kapton tape, which should allow us to heat the board to the set temperature that we want to set. So no longer feedback from the bottom and none from the board. So that's the great improvement by itself. It is set to 50. Let's set it to 120 degrees. Exactly. Okay, and now let's see how long until it heats up. So immediately we can see that our measurement is a little off, which is to be expected. We're gonna have to account for that. Why is it so different? We have 124 degrees on the board right now, while our feedback is saying 115. We got 130, while we have 120. Now let's let it stabilize. I do have a fan overhead and blowing with on minimum speed, so there is a little bit of air flow on the board. Oh, and our thermal feedback disconnected. Also to be expected. So this is nothing that we didn't expect. Let's see, it's still saying 120, while the board is at 144, 145, still growing. So this is something we have to account for. However, when I do this, I always watch the thermal image anyways. So, you know, it's not a huge issue. In this case, I would just, because we're at the 150, let's drop it to 106 right now. We're at 160. What is going on? So set temperature is at oh, this is set temperature. Let's drop to 50. Now it says it's 96 while it's 160. and the board is boiling 170. That is too high already. This 160, 170 degrees, that is close enough to even melting some solder alloys. Obviously a low melt solder will be flowing at this temperature, but it's a bit much. It's a bit much. This is not a thermal feedback that we can use. So this is point number one. We have to order a thermistor, a good, fast thermistor. This doesn't even seem like a thermistor. This is probably just a piece of metal that reacts to the temperature, which typically what thermistor is, right? It's a piece of resistive wire that changes resistance based on the temperature. But this one is extremely slow, and as far as accuracy, I don't see the accuracy here. This is just a matter of calibration, but in this case it's not even a matter of calibration per se. It's not like we're reading wrong. It's the contact that the thermistor has with the surface is not good enough to actually absorb that temperature. So right now we're 50 degrees off. We could account for that with calibration, for sure. But I think the better option is to just replace the thermistor with something a little quicker, something that absorbs temperature faster and doesn't need as great of a contact as this one needs. Alrighty, I guess we're gonna stop here, let it cool down. We have a plan. If you guys have any suggestions how to further modify it, because the case is still getting pretty hot, so what I want to do is just lift it like this, and this would be the position that will provide some more insulation and the ability for the air to just kind of go through underneath to cool it down. Perhaps I will put a fan to cool down the insides of the machine and just keep the temperature here, because obviously the temperature is going to be going up, not down. But as long as we're touching the case, the heater is physically touching the case, it needs to get hot. But before, it was touching the bottom of the case, so that's what was heating up the most, and the heat would go up. Now at least the top of the case will be heating up, but not from the bottom. Obviously the whole device got warm, right? So, you know, if you keep it on for 2 hours, there's no way you can use this device for 2 hours as it comes from the factory. Now maybe you can use it for an hour, hour and a half with this modification. But I want to make a modification so I can use it, so I can turn it on and use it for 6 hours. I can do 5 boards on one day, not waiting for this to cool down and stuff. So if you have any suggestions, definitely drop them in the comment. My first endeavor will be to find a better thermal feedback, and we'll see how that works. I will test the resistance, roughly what this resistance is, because thermistors come within different ranges, 10 ohms, 100 ohms, kilo ohms, whatever, and the resistance drops according to the temperature. All right, the higher the temperature, the lower the resistance usually. Yeah, that's what we're gonna do. So I have some conceptual work to do on this one, so I'm gonna start on that, and perhaps tomorrow I'll have something that will work, at least. We'll see. Now, as far as my updates, there aren't really any. I have an interview on Monday. The guy reached out to me from a very interesting company, actually. The WordPress, WooCommerce, Tumblr. That's what they do, supposedly. So that might be interesting. Another one that I applied to, what resonated me with interested me in the job listing was that they didn't list any particular technology, programming language, nothing. That is really awesome, because that's kind of my approach to software engineering. It's not like you become an expert in certain language. You're an engineer, so you should be able to work in any programming language, right? And that's their approach. That's why they didn't list it. It's like, you know, every new job brings new tools and new technologies and everything, and it is expected to have to learn stuff. I've never seen such a listing before, so this one really interested me, so I applied. So we'll see. I haven't heard anything back, but that was yesterday, so it might be still a little while. As far as 2 other prospects that I have, they're still prospecting. Haven't heard anything back. Obviously, I haven't heard anything back from the scam lady. Anyways, let's let this cool down and do some more work on it. Thank you guys very much for watching. I do appreciate you, and I shall see you in the next one.